Hi, thank you so much for clicking to watch this talk. My name is Cornelia Van Cott, and I work at the University of San Francisco. Before I get started, I want to give a big shout out to Micah and Rob and Sujoy for organizing this seminar. We really appreciate it. Okay, I'm excited to talk about my joint work. It's a project with Pat Shanahan and Jim Hosty. And the big picture of what we're trying to do is as follows. We're going to take two knots, K and J. And our question will be, if K and J are related in some way that we'll say in a minute, how are their crosscap numbers related? And we'll answer that in the special case when K and J are both two bridge knots. Okay, so to get off the ground, we want to first describe what's this relationship between K and J that we're interested in. It is as follows. Given the knots K and J, we want to know, does there exist an epimorphism from the knot group of K onto that of J? Okay, so let's think about this relationship just a little bit and get comfortable with it. So for example, like if I fix a knot K, there always exists at least one other knot J that fits into this scenario, and that would be the unknot. So that's good. Every knot has at least one such, any knot K has at least one such knot J. Okay, but for some knots, this is the only such epimorphism. And in this context, if a knot only has this one epimorphism onto the unknot and no others, then it's called minimal. And examples of such minimal knots are any knot with 6 or fewer crossings, and any knot, also another class of such knots is any knot that's fibered and has an irreducible Alexander polynomial. All right, and these are results that you can read about in work of Kitano and Suzuki. Okay, but of course, for other knots, there are epimorphisms onto other knot groups, and you can keep track of like how many there are and what's the large picture relationship among all knot groups in this way. And through this, there's been a conjecture, or there's actually many conjectures, but there's one that's called Simon's conjecture. And that is like, if you fix a knot K, let's count how many such epimorphisms there are. We know there's at least one, there could be more. And the conjecture was that there's only finitely many for any knot K. And this is called Simon's conjecture. All right, it's named Simon's conjecture after John Simon. And it's also listed in Kirby's list of problems. It's listed in problem 1.12, which has actually a small collection of problems about this relationship. All right, and this conjecture is proved true in 2012 by A.K.A and Liu. Okay. And another, I said this problem contains like a list of 4 different results. And this was one, proved true. Another conjecture in this list, also by Simon, asked how's the genera of the 2 knots relate to each other? All right, so it conjectured that if the knot group of K surjects onto that of J, then the genus has to be greater than or equal to that of J. And for those of you who maybe need a refresher, what does little g of K represent? It's the genus of the knot. So you're considering the minimal genus of all orientable surfaces with the knot K as their boundary. All right, so this conjecture, unlike the previous one, has not yet been proved true, but you can show that it's true in certain special cases. sorry for the extra noise. I live right in the Bay Area, and there's a bus that will go by every few minutes, but it will be by in a few seconds, so it won't last long. All right, so this conjecture was proved true in the special case when K and J are both alternating. And this actually doesn't take a ton of work. You can just think it through with me for a few seconds. If you have this relationship, the Alexander polynomials have a special relationship. So the Alexander polynomial of J will be a factor of the Alexander polynomial of K. It's always true. And if in addition, you know that K and J are alternating, you know that the degrees of the polynomials are related to the genus. So through those things, you can prove that this conjecture is true. Now, if you take an even more restricted look, instead of opening up to all alternating knots, but you restrict to a subset of just two bridge knots, then the statement can be made even stronger. All right, and what will it be strengthened to? We have the following result of Suzuki and Tran. And they say the following. All right, so you want to compare their result with what the conjecture is for all knots. So it's a conjecture that G of K is greater than or equal to genus of J. But if we restrict to two bridge knots, we get a much stronger inequality. Okay, that the genus of K is greater than or equal to 3 times the genus of J minus 1. All right, and this orange boxed result, this is true. This is giving you a relationship on orientable surfaces that K and J bound. So just a reminder, this is considering orientable surfaces. So in today's discussion, we want to flip that around and say, can I come up with a parallel result using non-orientable surfaces? Okay, that's today's goal. So in terms of non-orientable surfaces, we have an analog for genus. Genus is finding the minimal, the genus of a knot is finding the minimal genus of all orientable surfaces. When you flip to non-orientable, that's called crosscap number. I mentioned it briefly before, but now it's time to define it. All right, so it's going to be the minimal first Betti number of all the non-orientable surfaces in S3 that have boundary K. All right, so with that definition made, we can state an analog to the Suzuki-Tran result. So we'll have the same beginning to the theorem and then a relationship on crosscap numbers. All right, so we're given in a relationship between the crosscap numbers of K and J when they're having this relationship. And just to keep you comparing, if we're talking about orientable surfaces, this is our relationship down here. And now with non-orientable surfaces, this is our relationship. So you can see some similarities. All right. So rather than going through a blow-by-blow proof of this theorem, which may not do any of us as much good as something else, I'd rather do the following. If you look at this statement, there are three pieces to the puzzle. So I would say there's just like 3 things interlocking that have to all come together. And I think it'd be good if we just make sure we understand how each of those pieces of the puzzle work together. So let's see, what are the pieces? So one thing that we have is that we're working with 2 bridge knots. What do they bring to the table? What constraints do they have, and positives as well? So we want to discuss 2 bridge knots. What exactly are they and how do they work in this context? And then once we've done that, then we also have the other thing playing is, when do two-bridge knots have a surjection between their respective knot groups? So that's another piece of the picture. And then the final piece of the picture is, what about these surfaces, the non-orientable surfaces of two-bridge knots, related to two-bridge knots? All right, so this is how we'll proceed. We'll go through each one of these pieces of the puzzle, and then at the end, we'll put them all together and see how this is a reasonable statement, given how each of these things work. All right, so we're gonna start it off by understanding two-bridge knots. All right, so any two-bridge knot can be expressed in a certain template. So let me draw that template for you. Actually, there's two templates for how a two-bridge knot diagram can look. All right, so when I'm drawing these little boxes, of course, that means you have AI as an integer. So you have AI twists between the two strands that go into the box. And so you have all these little twist regions. If you have an odd number of twist regions, then this is the template for how you close it back up. And if K is even, this is the template for how you close it back up. Of course, when I have AI, it could be a positive or a negative number. And that will determine whether or not they're left or right-handed twists. So that's a detail that should be smoothed out if we're writing a paper, or if we had lots of time. But right now, that's not super important. All we need to know is that there is a convention out there that we could nail down about whether or not it's right or left-handed twist, but it's just the number of twists is given in this box. That's part of it. Okay, and given this, we can denote any two-bridge knot by just simply telling someone these twist numbers. That will determine the twist knot, the two-bridge knot. So we denote it by A1, A2, just telling those numbers will determine this knot, if we knew all those details. Okay, and sometimes we'll just write the vector this way. So that vector determines a two-bridge knot, a vector of integers. All right, and now there's a valuable connection between two-bridge knots and rational knots. That we want to mention. Did I say rational knots? I meant rational numbers. Rational numbers. Here we go. So given a two-bridge knot, we can get a rational number as follows. So say I have some two-bridge knot, which is determined by this vector of numbers, of integers. Then I can get an associated rational number by considering the continued fraction expansion given by, or determined by, these integers. So start with 1 over A1 plus 1 over A2 and keep on going. There, that's going to determine some rational number P over Q. Okay, and then the reverse direction goes along as well, that if you have a fraction, and if Q has to be odd in order to get a knot, and P less than Q, and it has to be or take it to be relatively prime, then if you take a continued fraction expansion for P over Q, that will determine a knot. So you find a continued fraction expansion, and that will determine a two-bridge knot. And again, like I said, we'll denote it K of P over Q, because that will tell you how to do these twist regions. Alrighty, so a natural question, if you haven't seen this before, a natural, great question to ask is, oh, so if I have this rational number and I have another rational number, is it possible that two different rational numbers satisfying this condition could give me the same two-bridge knot? It is possible, and that relationship is fully understood. It's quite a beautiful relationship that we have between these two worlds. But I think that for now, we have all we need to move on. This is our piece of the puzzle for two-bridge knots and what sorts of ways we can talk about them. So we're going to move on to our second piece of the puzzle, which was knowing when two bridge knots have an epimorphism between their knot groups. All right. All right. So in order for us to get off the ground here, I'm going to give you one visual example where it does work out. I'm going to give you a two bridge knot J and a two bridge knot K and indicate to you how you have this epimorphism on their knot groups. All right, so we'll do a visual example. All right, so I'm going to start off by allowing you to choose any two bridge knot J you like. Anything. So I'm just going to put a big block here and say you can fill that in any way you feel. And I'm going to draw it in what's called the four-plat configuration. So it's going to look like this on the top and bottom. This is J. And just to emphasize, anything can go in here. We'll just write, this is some braid of your choice. All right, and using this, I'm going to construct a knot, a two bridge knot K. Here's how that construction goes. Let's take this braid and take an odd number of copies of the braid. So I'm going to take 3 just because it makes the picture easier. You can take any odd number. Okay, so each of those represents the braid. And then every other one, I'm going to rotate by 180 degrees. So these are in the same orientation. And this one is in opposite orientation, rotated by 180 degrees. All right. And now at the top, I'm going to close it up just like I did before. And in between, we call these the connector regions between the copies of the braid. In between, we're allowed to put any even number of your choice, any even number of twists between those center strands. So I didn't leave myself enough room, so I'm just going to put 2 twists between the center strands. But this can be any even number. All right, in this way, I've constructed a two bridge knot K. So I've got K, I've got J. And now I'd like to justify for you how it is that these are examples of a space where I can have a knot from this pair to this pair that induces an epimorphism on fundamental group. Let me explain how that can work. So we're going to take this copy of S3 and slice it up into 3 domains. So you can imagine this is all of S3, and I'm going to slice it with this plane and then this plane. So I have the top, the braid, and the bottom. Similarly, I'm going to slice this copy of S3 with K inside of it into domains as well. And then I can define the map on each domain individually, and it will give a map of the whole space altogether. Now there's going to be a few details that I can't fully explain. This is all written down very nicely by other people than me. But hopefully the picture is still really helpful. How will we map this space onto this? Well, some domains are easy to anticipate. You can anticipate this domain just maps right on over to this one right here. And hopefully you can similarly anticipate that this bottom region maps quite easily onto this bottom region right here. No worries. And then of course the braid regions, they can map right over, and this braid that's been rotated by 180 degrees, just rotate it right back by 180 degrees and maps right over to this region, no problem. So the only thing to worry about then is the connector regions, these places where we have an even number of crossings. So what we want to do is a quotient by a 180 degree rotation. And so that you're going to consider a 180 degree rotation about this line here that cuts through halfway through the twists. It's an even number of twists, so we can find a halfway point. And consider doing a 180 degree rotation. And quotient by that, same down here, 180 degree rotation. All right, so let's imagine these purple lines. What happens when we do that 180-degree rotation to those purple lines? What will happen in the end will look something like this, which can be isotoped to look like this, and so can map down to be this, to this domain. Similarly, this region, do that same quotient, and you're going to be able to map it up here. So you're just going to move down this K construction you have as I've described. So now I just want to say one more time, this is not every single detail, but I hope it's enough for you to feel that you can see this example of two bridge knots where I can get a map of the spaces as I want. The reason why I was so excited to show you this example is that actually, the amazing thing is this is the only such example. If you have any two bridge knots that have this relationship, it has to fall into this template. This is a result that was proved by a large number of people in stages. And when I write it down, it might be a little overwhelming because it takes a lot of words to say what we see here. That's why I want to show you the picture first. So now you have the picture in your mind of what J and K look like. So when you see it in words, you can interpret it more readily. Okay, so now let me write down for you the theorem. Okay, we barely fit that into the screen, huh? There it all is. You can see all the names of the people who've contributed and the result all in one picture. And it could seem overwhelming, but let me point out the familiar parts that you can pull back in by remembering this picture. It's saying that if you have this epimorphism, then this fraction corresponding to K, it just can't be anything. J can be anything. But the fraction of K has to have every other, you can see this is including the fraction for J in every other spot. So you observe that here when I have the braid alternating with even numbers of twists. So these are the connector regions where there's an even number of twists in the center. These are the braids. There's an odd number of braid copies, and every other braid is flipped around. That's why this is A inverse. So it means that the numbers go in the opposite direction. Okay, and I wrote that there's fine print about the possibility that if the connector is 0, you do a couple extra things. But really, it's nothing to change the main fact, which I hope you feel settled on, is that everything looks basically like this picture. Okay, so this is pretty strong and complete answer to the question of when are there epimorphisms. It's an if and only if statement. All right, that concludes our second piece of the puzzle, understanding the epimorphisms, and we're ready for the third piece, the final piece of the puzzle. And that is understanding two bridge knots and their surfaces. All right. The nice thing about two bridge knots is that if you just draw their standard diagram, that template that I drew for you earlier, there's an obvious surface that that diagram has associated to it. And it has a lot of nice properties. So we're going to starting there. You know, the obvious surfaces, that's the right place to start. So let me draw the template with 3 twist regions, the same, it will be similar for any number of twist regions. So let's do an example. Now, to stick with the template, I should connect this in this direction, but in order to see the surface, I'm going to connect it this way. All right, so the surface that it bounds will have 3 twisted bands. So this is the 2-bridge knot A1, A2, A3. And so we're going to get a surface F that's going to have 3 twisted bands, and the number of twists will be these same twist numbers. Let me draw that for you now. Okay, so hopefully you can visualize now that we have 3 twisted bands and they are plumbed together. And more generally, we could do the same sort of construction. Oh, also, and hopefully you can see that the boundary is the same as this knot over here. And we can do this construction in general. So if we have a continued fraction expansion for P over Q that has numbers A1, A2, all the way out to A sub R, then all right. And the nice thing about these surfaces is that you can readily tell just in a blink whether or not the surface you're creating here is going to be orientable or non-orientable. It's just by checking the parity of these twists on the bands. So if all the numbers, all the AIs are even, you'll be creating an orientable surface. Otherwise, non-orientable. All right, and then I want to say one extra little comment, and that is, suppose you do this whole construction and you end up with an orientable surface. Then there's a very easy change you can make to the surface that doesn't change the knot that it bounds, it. But it just changes the surface to make it non-orientable. So let me point that out to you. Let's say this is orientable. If I just add a twisted band like this, it corresponds to doing a Reidemeister 2 move to the knot. So it doesn't change the knot. But this little extra thing makes the surface non-orientable. Okay, so we'll do that a couple times. We'll say if the surface is orientable, we can make it non-orientable by adding a band. Okay, so we cannot be so presumptuous to think that the surfaces we create with this nice, obvious connection will necessarily realize genus or crosscap number. You definitely can't count on that. However, in this case, we're so lucky that the construction does do that. So this kind of construction where you start off with the standard template and find the surface, it can create the crosscap number surface, the surface that computes the crosscap number, and same for genus. So I'm going to write down these nice, beautiful results that state that. Next, the first one is the result of Gabai. All right. So with Gabai's result, computes the genus of 2-bridge knots. You just have to take your fraction and find the continued fraction expansion that has all even non-zero entries. Such an expansion exists and is unique. And then if you form the corresponding circle, oh, I made a mistake. This isn't R. I'm glad I recognize this, since no one in the crowd could tell me I made that mistake. So if you do that, the length of that continued fraction expansion will always be 2R. It'll always be an even number. And so then the genus of the surface will just be R. Okay. And the surface that we're looking for will be the one that corresponds to this, where you just take the twisted bands and they're all even, so it'll be an orientable surface, and it's the one you're looking for. Okay. And then we have the corresponding computation for crosscap number by Hirasawa and Teragaito. Okay, so here's how this result goes. It says, instead of finding this one with all even numbers, you just need to find the continued fraction expansion that's shortest length, so as short as possible. And then the crosscap number will be related to this as follows. So if this surface that comes from this expansion, if it's already orientable, non-orientable, then that will realize the crosscap number. And remember, it's really easy to look at these numbers and know if it's non-orientable, just if any of them are odd. So the crosscap number will be R if there exists a B sub I that's odd. Okay. Now, what if they're all even? If they're all even, then that's going to be an orientable surface, and we'd like a non-orientable surface. So what we have to consider are options here. Turns out, if they're all even, but one of them is 2 in magnitude, then there's a workaround that you can do with continued fraction algebra to get one of the numbers to be odd. So it's also equal to R if there exists a B sub I with magnitude 2. There's a workaround that you can still fix this up. All right, but if all the entries in here, if they're all even and greater than or equal to 4 in magnitude, there's no workaround. And in order to make it a non-orientable surface, you have to do that little trick that I mentioned before to take your orientable surface and add an extra band to make it non-orientable. And so the crosscap number ends up being R plus 1 in that case. All right, so we have our genus computation and our crosscap number computation. Pretty nice results. So now we're ready. We've gone over the 3 puzzle pieces. We're ready to put everything together to now understand how the main result of today is true. So I expect that most of us have long since forgotten what the main result even said, because so much has happened in the intervening time. So let me just rewrite it down so that we all have it in mind. There we go again. That's what we had to start. And now, hopefully, you're facing this result with a lot more understanding. You know exactly what we're working with. When I say 2 bridge knots, you know that template. And if they're not only 2 bridge knots, but they have this relationship, we're even more restricted. K and J can only have a certain look. You have that picture in your head. And we have a plan on how to compute crosscap number and what sorts of surfaces will realize that. Okay, so now let's see what makes sense here. I want to tell you what the biggest roadblock to proving this theorem would be, because you probably don't have intuition like, so what's going to be the rough spot? The rough spot will be the following thing. Let me bring back this theorem of how to compute crosscap number. You see, in this theorem, we have to take P over Q and find the shortest length continued fraction expansion. And I didn't say anything about it earlier, but it actually is an unpredictable, there's an algorithm to find it, but it's rather unpredictable and difficult to implement, especially difficult when you want to keep control of 2 knots at the same time to compare their crosscap numbers. So this is the biggest roadblock, is finding the shortest length continued fraction in order to compute the crosscap number. All right, So that was the hardest thing. And how did we get around that roadblock? This is the most significant part. So let me bring back the theorem. In order to compute crosscap number, you need to find this. So we found ourselves doing was always being jealous of Gabai's result. He was able to compute the genus. He didn't have to worry about this down here. He just had to find the continued fraction expansion that had all even non-zero entries. It's much easier to compute. It's unique. It just comes from the Euclidean algorithm, basically. So we were jealous. And so we wondered, you know what? I wonder if we can recast this result and compute crosscap number, not from this continued fraction expansion, but from the one Gabai used. And in fact, that's what we were able to do. So that's the first lemma along the way of proving our result. All right, so once we have this, it's basically like you're in the roller coaster and you've gotten to the top of the hill. It's all downhill from there. Things work out a lot better once we were able to get around the roadblock. Okay, so let me indicate that for you now. Okay, so here's how it can go. Let's suppose you have an epimorphism. Okay, here's the path to take. The first thing you do is find the even continued fraction expansion for J. So remember, J could be anything. So find the even continued fraction expansion for J. All right, and then using our lemma, our workaround, we are able to directly from this, we're all ready to go. Using our lemma, we're able to compute gamma of J right off the bat. We're good. Okay, now what's the next step? Next step, we go over here and remember that there's a very specific continued fraction expansion for P over Q because it has to have that very special format for K. So recall by our previous result, so P over Q has a continued fraction expansion that has A in every other, or A inverse in every other entry. And in between it has these connector numbers, remember? So what's the wonderful thing? Well, we already know A already has all even entries. And these connector numbers are forced to also be even entries. So we automatically have an even continued fraction expansion. All these numbers are automatically even. So that's our big celebration. So they're all even numbers, even without trying. Okay, so right away, we can apply the same lemma, apply our lemma to this situation and compute gamma of K. So if we didn't have this lemma, we'd be hunting for the shortest length continued fraction expansion, which is just this long process. But here it's just falling right out. The only caveat is that some of these connectors could be zero, not just a non-zero number, it could be zero. So there has to be a little give and take, but that can be mended quite easily in this whole scheme of things. All right, so we have both of these values. And then, because everything was so controlled in this whole situation, we're able to compare that it has to be at least 3 times gamma of J minus 4. That's the main arc of how we could get so much done. Okay, what I'd like to point out to you right now is you might wonder, well, where did this 3 come in? It was in the genus, the orientable result of Suzuki and Tran. How do we get a 3? And I can say exactly where it comes from. Remember when I said, when we're making this K and J template, I said that this braid has to be repeated 3 or more times, and an odd number of times, and at least 3. So that's why we have 3 copies of the braid from J. So those 3 or more copies is where we get this lower bound having a 3 in front of it. All right, so like I said at the beginning, this is, or I think I said it at the beginning, but if I didn't, I'll say it now. This inequality is sharp. We can give you an infinite family of examples where it's an equality, not an inequality. Let me do that for you now. You consider the 2-bridge knot corresponding to 4n at continued fraction expansion, or draw the template for it too. And then, oh, whoops. This should be J. That's the downstairs 2-bridge knot. And then K upstairs is going to have that braid 4n, and then the connector 0. And then 4n, and then another connector 0, and finally 4n. That's an infinite family of 2-bridge knots, and it's in the format so that this knot group will surject onto that one. And if I compute gamma using our lemma, gamma here will be 3, and gamma here will be 5 for all n. And you can observe that that will make this inequality into an equality. So you can't improve on this. And again, I might have mentioned it before, but it might be interesting to say, well, could I expand this set of knots for which this inequality is true? It's true for 2-bridge knots. Could I go any bigger? And we have examples of 1 2-bridge knot and 1 alternating knot. So you just split it, 1 2-bridge and 1 alternating that's not 2-bridge, and the inequality is no longer true. So it does seem to be something special about 2-bridge knots. All right, you have a gold star right now if you are still watching. Thank you so much. I hope that you have a better picture in your head for how these things work together. If you want more details, I'd love to talk to you more, of course, and you can also take a look at our paper that's posted. And again, thank you so much for listening. I really appreciate it, and I hope you have a great day.